behavioral patterns. Um, and so last time we have seen the observer pattern, and we have seen how to improve it a little bit and how to make it slightly different. We have seen also chain of responsibility, which is basically one way to follow a chain of possible targets of one function call until we find one. And today instead we are going to look at visitor. So visitor is one of the most complex programming patterns, also one of the programming patterns which is has been the focus of some criticism. So we're going to look at visitor and see how does it work. So let's start with an example. So consider a compiler that internally will represent a program as an abstract syntax tree. So internally the program is going to contain a tree of elements which represent the structure of the program. So the compiler takes a text file, it parses it, and stores it in memory as a tree. And this tree is called the abstract syntax tree. The syntax tree contains in each node elements of the program. So the idea is that every node has a slightly different type. So there will be nodes of type variable, for example, nodes of type operation, nodes of type numerical constant, and so on. Okay? So the abstract syntax tree is the internal representation of a certain program, and it's the shape of a tree, so it's a tree data structure, and every node in the tree is a class belonging to a hierarchy of classes. Okay? Then we want to perform syntax checking of this tree. So we would like to see if the program is actually correct. So we want to go and explore the data structure to see if the structure is correct. So if there is some error in the program or not. Or maybe we want to also to generate code. So again, we have to explore the syntax tree to produce the final assembler code that is going to be executed. Or we may want to do some other kind of analysis. For example, maybe we want to print the program in a nice formatted way. Or we want to transform the program to optimize it. So in general, you have on one side a complex data structure, in this case an abstract syntax tree, and on the other side you want to do several things with this data structure, so you have different kinds of operation. Okay. This pattern is called visitor because what you need to do for every operation is to visit the data structure and do something slightly different. Okay, so on one side you have this structure, and the structure might consist of different types of nodes, for example, implemented using the composite pattern. And on the other side you have the need to explore the data structure and perform some operation that can be different for every different kind of functionality you want to implement. So let's see the naive approach first. So how would you structure this? So the most simple way of structuring this is to have the data structure implemented as a hierarchy of classes. So you have a generic node, a class node, which is an abstract class, and from there you derive several different classes. The class node will implement one virtual function for every kind of operation you want to implement. For example, type check or generate code. or pretty print. Okay, and then every single kind of node will implement its own version of the type check, the generate the code, and the pretty print. Okay, and then what you do is that you go through the tree, for example, the abstract syntax tree, and you call the functions that you want to call. For example, if you want to do type check, you explore the tree in a certain order, and then you call type check on each node. And if you want to generate code, you go through the tree and you call generate code on each node, and so on. Okay, so you implement the operation as a function, in this case a virtual function, directly in the data structure. Okay, so this is the naive approach, the simplest one, the most direct. Why is not very, very good? It's not very, very good because I would not say it's not correct, actually. Here I wrote in the slide it's not correct. Actually, it's not about correctness. It's about opportunity to do this. In particular, this approach does not scale because if you want to implement one more operation on the data structure, you need to change the node class, adding one more virtual function, and implement this virtual function everywhere in the derived classes. Okay, so basically you need to change all classes derived from node. Also, this is against the single responsibility, because you have one class that does many things at the same time. So you are mixing representation of the data structure, operations in the data structure like adding and removing nodes, and operation on the data structure like visiting and doing type check and everything. So every class now here does many things at the same time. This is against the single responsibility principle because you are basically coupling together many things in the same class. So what we want to do is to find a way to decouple visiting from nodes. In particular, I would like to implement the operation in a different class. Okay, so we would like to separate the operation that are on the node, for example, all the operations they have to do with the composite pattern, from the operation they have to be done on the entire data structures, like visiting and doing the type check. Okay. So the pattern we are going to propose is called visitor because we are going to visit the data structure, and every time we visit the data structure we do something different. The idea is that we do a different hierarchy of classes that we call node visitor. And these node visitor classes will provide functions for visiting the different kinds of nodes. For example, if you have an assignment node in the original hierarchy, then here you have a visit assignment. And if you have a variable ref node, here you have a visit variable ref. Okay? So for every kind of node, you are going to have one function. And this is the abstract class that every visitor has to implement. Then different visitors will implement different operations. For example, you are going to have the type checking visitor, which will implement visit assignment, visit variable ref. And the code generator visitor is going to again implement his own version of visit assignment and visit variable ref. Okay? So what happened is that in the previous case, the operation were together with the original node classes. Now we are going to separate these, okay, and distribute them in a different way. You are going to distribute them in a different hierarchy of classes, the visitor hierarchy. And for every type of node, you are going to have a different visit function. So in the node, you are going to have one function that you call accept, that takes as parameter a reference or a pointer to a node visitor. And every single node has to implement this accept function, accepting a node visitor. Okay? Now, the node class is simpler because it only has to care about accepting visitors and only needs to provide a hook for allowing visitor to visit it with this accept function. And what this accept function is going to do? Well, it does only one thing. It calls the corresponding visit function in the previous hierarchy. For example, node visitor implements visit assignment, and visit assignment is also implemented by the type checking visitor. So what we are going to do is that when we visit an assignment node, we call its accept by passing a reference to the type check visitor. And this accept function will, in turn, call the visit assignment of the type checking visitor. Okay? So this is the complete pattern. Sorry. You have on the top, you have the visitor hierarchy. One visitor generic, which implements one visit for every type of concrete element. And then you are going to have several concrete visitors, one per every operation you want to implement. The client accesses the object structure, in this case a tree, and the object structure is composed by elements. Every element implements an accept, which takes as parameter a reference to a visitor. And in every concrete element, in addition to the normal operation of a concrete element, will accept a visitor. And this accept calls the corresponding visit in the visitor hierarchy. Let's see also the sequence of function calls you are going to have in this pattern. So you have the object structure. You are going to visit the object structure in some way. For example, first the nodes from left to right, and then the parents. Okay, so while you visit the object structure, you call the accept on the concrete element by passing a visitor. The accept will call the visit concrete element A of the concrete visitor 1. This in turn can do something on the concrete element. For example, can ask for information or can modify the element, whatever. Okay, then we complete this, we go in the object structure, and we are going to visit a different concrete element B. So we call the accept on the concrete element B, which calls the visit concrete element B on the concrete visitor 1, which in turn may call the operation B, and so on. And this for every concrete element in the hierarchy. Okay? Okay, so when this visitor pattern has to be used, when you have an object structure which contains many classes of objects with different interfaces, and you want to perform operation on the elements of the structure, and also when many different operations need to be performed on objects in a structure, and you want to avoid putting such operations in the object because you want to decouple. And also, it's useful to have this visitor pattern when the classes defining the object structure rarely or never change. So when this hierarchy here doesn't change much, it's okay to implement the visitor pattern. Otherwise, you may have some trouble. Why? Because as you can see here, in the visitor base class, you have one virtual function for every concrete element in the hierarchy. So if at some point you decide to, later on, you decide to add one new element in the hierarchy, unfortunately, the visitor hierarchy changes a lot because now you need to implement one new visit function in every class. So you actually have a lot of work to do. So if this element hierarchy changes a lot, then the visitor pattern is probably not the best solution to the problem. Instead, if the element hierarchy doesn't change at all, or it changes very little, then it's okay to use the visitor pattern because you don't need to change these functions. Okay? So, visitor makes adding a new operation easier because adding a new operation means that you have to add one new concrete visitor class in this hierarchy. Just that. Unfortunately, on the other side, adding a new concrete element is hard because, as I said, you have to go back and modify every single visitor. This pattern is a little bit similar to an iterator. However, the iterator visits the element of the same type. For example, all elements in a vector will have the same type, and the iterator goes through all the elements of a vector. On the contrary, a visitor traverses structures of objects of different types. Also, the iterator is about visiting, while the visitor pattern is not about visiting. It's about performing operation while visiting. So basically, iterator and visitor can be combined. Iterator can be used for going from one object structure, concrete element to another concrete element. So you can define, for example, your own iterator for exploring a tree. And once you are, while you are exploring a tree, you can call the visitor to perform operation on the elements of the tree. One advantage of using visitor is that you can accumulate state. In fact, the visitor is an object, so while it visits the hierarchy, it can accumulate state or cross-check the structure. If you implement the operation in every element, you cannot keep the state of the current visit inside these functions, of course. You need some global object to take care of the current state of the visit. With visitor, it's much easier because this is a class. It can contain data, and while the data structure is visited, this function are going to be called. So I can check what's going on during the visit. For example, I can check that an assignment always contains on the left side a variable and never an expression. I can do that because while visiting the assignment, I can check that on one side there is variable, on the other side there is an expression. Okay? It's much more difficult to do this in this structure because you don't have any global place where to put this information. You need to make one. Here instead it's already there. So you have some state that can be carried on and updated while visiting the data structure. So you can accumulate state. Okay. The visitor is able to understand the type of element it is visiting using one technique which is called double dispatch. Double dispatch means that the function that is going to be called depends on the type of two objects. In single dispatch, the operation to be invoked depends on the type of the object or of the pointer to the object and the parameters list. So, for example, virtual functions are used to implement the so-called single dispatch. Okay? What does it mean? I have a pointer to the base class, which points to any object that can be derived from the base class, of course. And when I call a virtual function, the version of the function for that specific type of object is going to be called. So depending on the type of the dynamic type of the object, I choose which function to call. So single dispatch is the virtual function, basically. Okay? In object-oriented slang, we say that it depends on the message type, so the name of the method and the parameters list, and on the receiver, so the object. Okay? Double dispatch, instead, is when we want to select which function to call depending on the type of two objects. And in particular, here we have the visitor and the element. We need to understand which function to call depending on the type of the visitor and on the type of the element. This is realized in C++ using the accept. Accept is a double dispatch operation because the final method that is going to be called depends both on the visitor type and on the element type. Okay? The technique used for the template observer, the one that we developed last time, is quite similar. Which operation is invoked depends on the message type, update, on the receiver, the observer, and on the subject, parameter of the update. Okay? So double dispatch means the function to be selected depends on the type of two elements. In this pattern, it depends on the concrete element. Here I call visit concrete element A, and here I call visit concrete element B. So it depends on which concrete element I'm visiting. But also it depends on the concrete visitor. Here I'm calling visit concrete element A of concrete visitor 1. And here I'm calling visit concrete element B of concrete visitor 1. So this accept is called double dispatch function. Okay? Who performs the visit? Of course, there are different techniques. It can be the visitor itself that moves from one element to the other. It can be a separate object, for example, an iterator, which decides how to visit the data structure. Or it can be a specific method encoded in the object structure. So you can choose different techniques for doing that. Okay, so we are going to look at some code now. Okay, so here we have our hierarchy. So first of all, I define some elements that I want to visit. I do this a forward declaration of the elements. These are needed because I need to implement the visits, to declare the visits here. Okay. Then I define class visitor, which is the base of the visitor hierarchy, and it has a virtual, I forgot to add here, virtual destructor visitor, and then many virtual function visit, which take as a parameter a variable ref node, then visit that takes as a parameter number node, assignment node, and sum node. I use the same name visit, okay, because it's shorter, and C++ still understands, because all these are different functions because they have different parameters. So these are virtual functions that have different parameters, and I didn't implement them. They're just empty now. Okay, so this is the declaration of the base class of the visitor hierarchy. And now I'm going to present you the hierarchy of elements. So I have a class node, which is the base class of the hierarchy, and I just use a string type to memorize, to store a string that identifies the type. Okay, and then I have a node, which takes a string and stores that in the type, and then a virtual destructor. Then I have a get type for getting the internal type, and then I have a L value, which is a boolean. It tells me if this is a left value or not. And then I have a isLeaf, which is a boolean, and by default it returns true. And finally, I have the accept, which is the double dispatch technique, which takes a visitor, a pointer to a visitor. Then I want to implement the composite pattern, so I have a class composite node, derives from node, and is not a leaf, of course, and I implement a tree, so I want to store a left and a right element in the composite node. Okay. Then I have a macro which is going to implement the accept in the nodes. I don't want to write void accept v visit this all the time, so its code is going to be the same everywhere. So I just define accept. Okay, just for saving some typing. And then variable ref node derives from node, and it's a leaf. So well, it's a variable with a certain name. It can be a left value, so it can be at the left of an assignment, and I'm going to return the name, and I define accept. So this text is going to be copied here, so the variable node implements the accept. Notice that the accept has always the same code for every derived element. Then I have a number node, again it's a leaf and has a number inside. Then I have a binary operator. A binary operator contains a left and a right, and I have a string which represents the operator. Okay, and well, I can set the left and the right node, and I say that this is not a left value because an expression cannot be a left value, and I can get left and right. Then I have an assignment, which is just a binary operator where the symbol is equal. Then I have a sum, and I have a plus here, and that's it. Okay, so this is my hierarchy, and then later on I will see how to construct an expression using these classes. Okay. Here is the visitors. This is a visitor for generating code. Well, it doesn't generate anything. It actually visits the hierarchy and prints something on the output. So it's not really a code generator, of course. Here I have a type check. Type check is going to store internally in variable error if I find an error. And when I visit a variable ref node, I'm going to say OK. When I visit a number node, I'm going to say OK. When I visit an assignment, I check if left is 0, then it means I'm missing left value in assignment, and I put error equal to 0. If is not L is not an L value, then I print error. This one is not an L value in assignment, and then error true. And finally, I have a visit of a sum. It's OK. Actually, I should check also that the sum, I have the correct type of things left and right, but I'm not going to do it now. And I also implement the functions for visiting. So I do in order visit is going to go from left to right. So if it's a recursive function, so I take a node and a visitor. If I am on a leaf, I just accept the visitor. Else, what I do is that I convert the node into a composite node. Okay, if doesn't convert, there is an error because it should be a composite. And then if I have a left, I do in order visit of the left part. Then I accept the current node, and then if there is a right, I do in order visit of the right subtree. Okay, so this is in order because it first visits the left part, then it visits the current node, and then it visits the right part. If I want to do some post-order visit, then I do the other way around. I first accept the node, and then I accept left and right. And if I want to do a pre-order visit, I first accept left and right, and then the current node. Okay? And then function GenCode is going to create a visitor type generated code, and then call in order visit on the node, on the root node. And type check is going to create a visitor type check and visit in order the type check. And if there is an error occurred. And then finally the main, I just create an assignment node. I put a variable, a node 10 and 20, and a sum. And then I organize the tree in this way. So basically I first build the subtree for the sum by putting on the left 10 and on the right 20. Then the assignment node, on the left there is the variable, and on the right there is the sum. And then I do type check of the assignment node and generate code for the assignment node. Okay? So we are ready to compile now. Okay, so the printing is probably not very meaningful, but this is an example with visitor pattern. It prints x, which is the name of the variable, okay, 10, okay, sum, okay, 20, okay, and then x equal 10, 20. I didn't add the end, the carriage return, so this is all printed one after the other. And let's try now to cause an error. Suppose that, I don't know, I swap left and right here. I put the variable to the right, and I put the sum to the left. Okay, and so I have an error. Error, sum is not a left value in assignment. Okay, so an error occurred. Okay, did you understand? So I have a question for you now. Let's see if you understand. I said that this accept function is always the same for every element in the hierarchy of elements. So I defined this macro here. So the question is, why I didn't implement that in the node? If it's always the same, why I don't implement this in the node? Did you understand the question?
Yes. Yeah.
So accept, the code for accept looks like it's always the same. So why I don't implement that in the node? So that everybody inherits the same code. So the answer must be that it's not the same code. But why is not the same code? Obviously, right? I mean, if I do this, there must be a reason. And the reason is it's surely that it's not the same code, right? Otherwise, it would be stupid to repeat the same code everywhere in the derived classes. So why it's not the same code?
This is different.
Exactly. So these has a different type. In the node class, this is of type node. In the derived classes, this is of type element. So variable ref in variable ref, number node in number node, and so on. Okay? If I put this in the node, even if I am on a specific object like variable ref, the fact that accept has been implemented in the node means that the type of this is pointer to node. Okay? So when selecting which version of visit to call, it will look for a visit that takes a node, a pointer to node, and there is none. Okay? If you want, we can go back and write here visit variable, visit number, visit assignment, visit sum. This means that here I need to put something here. For example, visit assignment. But I have to put visit assignment in the assignment class. I have to put visit variable in the variable class, and so on. Okay? To simplify a little bit, I just defined a macro, and if I define a macro, I have to put the same name everywhere. But this doesn't mean that it's the same function. It's actually 4 different functions, and which one is going to be called depends on the type of the parameter. And the type of the parameter is only known inside the element. So is it clear?
Mm.
Do you have doubts? So if I put this accept into the node class. Okay, this is of type node. The compiler looks at the type of this, has no idea which object this is, so this is of static type node star. So it looks for a visit that takes a node star, and there is none. So I cannot do this, unfortunately. Okay? So I need to repeat the accept for every single element class that I want to visit. Okay? I didn't do that for binary operator because binary operator cannot be instantiated actually. Because there is no generic binary operator, there is a sum or assignment. So I have to define accept for assignment and for sum. Okay? Notice that here I had to I put everything in one single file. If I want to separate in different files, it's not so easy because class. So the visitor has to know the base class of the visitor hierarchy has to know all the classes of the elements hierarchy. And this is why here we said that the classes define the structure rarely or never change, because there is a strong coupling between the visitor class definition and all the classes in the hierarchy. And this strong coupling is basically very difficult to avoid. Okay?
Excuse me.
Yes.
Is there a way to not use the define, because using the define the code is not compiled?
Sorry, I don't understand the question.
Is there a way to write the define in a way that the code defined is compiled?
The code is compiled because the define is processed by the pre-compiler. The preprocessor is executed before the compilation begins, and the preprocessor is going to solve all defines, all includes, everything. And the define is solved by copying this text inside here.
Yeah, right.
Okay, so I'm going to show you how does it work. So if you run the compiler with -e, actually what happens is that only the preprocessor is run. Where is it? Here. Okay, and this is the output of the preprocessor, which is then done as input to the compiler. And as you can see, is solves the include. Okay, then it solves of all the standard includes, which are very long, so we are going to skip all these. This is only the standard includes. As you can see, all the standard includes are copied into the file. So the file becomes very large because it's going to include everything, basically. Yeah. At the end, you find our code. As you can see, there is no define anymore. And instead, for example, some node has this text copied in it. Okay, so the text is actually compiled. The only thing is that is before starting, it does a copy and paste. Here, see?
Yeah. Okay. Thank you.
And that's it. You can use actually a template for doing the same thing that is done with the define. We are going to see very soon how does it work, but the idea is that you define a function accept, which is not going to be virtual, but is going to be static, and this accept is going to take to be templatized with respect to its own type. So it's a little bit strange, but we're going to see in a while. So, but right now let's have a break so you can think a little bit more, and then we are going to see two more applications of the visitor pattern. So let's have a break of 10 minutes.
Oggi ne abbiamo uno. Sì, oggi c'è CBSD.
Never going back.
He's going back. Go. Yes.
Excuse me, Professor, are you listening?
Yes.
Can I have a question about the final project? The next assignment deadline will be at the end of the month, more or less.
The deadline will be the exam.
Okay, the exam. And the final project for the exam, it will be a fourth assignment, or is the third?
No, it's the third. The third is the last, and it's actually the final exam.
Okay, plus an oral evaluation, maybe with...
Yes, during the oral I'm going to ask some questions about the course, like patterns or, I don't know, some technique, and then I'm going to discuss the project.
Okay. Do you know approximately the exam dates?
So I've not completely decided them now, but I'm going to do that next week. So basically, I think will be first week of June or something like that.
Okay. Thank you very much.
Yeah, and then of course it's not the only one. There will be another one more or less end of June, and another one mid of July.
Okay. Perfect. Thank you very much.
Okay.
Professor, can I ask you one question? About the final mark, what would affect the final mark? The assignment and the project both, or just the final exam?
Yes, so a big part of the mark is going to be about the assignment, the final assignment. The first and the second doesn't count too much, but the last is going to count a lot. And of course, also the oral.
Okay, thank you.
Lì sì, no, si sa il film non è quello lì. Poi disegnato su stampa. Ah, ok, non c'ho avuto e mi ci ho messo basta, io
Stress, sì, poi insomma, 2 settimane di integrazione, eccetera, io lavoro alle 8:30, esco alle 8, bene.
questa mese invece mi sono frenato 3 giorni di fatto al lavoro, quando i giorni che erano dal ritorno di Pasqua fino a prima.
Io ero a Freddo, quindi perso un giorno,
Tanto tu anche.
c'avevo da 4,
Faccio qualcosa di bello.
No, è solo più maggio.
Non penso.
No. No, così no. Sì, questo ho fatto una.
Sì.
Testi di un su cui nascono di adesso tutti con le uguali alcuni di vari tools, diciamo delle funzioni sono delle aree che tipo inserisci e non ti lasciano uguali ma non e tu si sveglia il tuo, cioè, nel senso che c'è un istituisci
quindi l'ho piazzato e quando la riserata sullo stato e quando la riserata appunto c'è questo è il fatto. Sì, ma è stato
per uguale, come c'è la possibilità.
Okay, so we continue. We actually continue analyzing a little bit more this pattern. In particular, I would like to discuss for this for making visitor a little bit more useful, let's say. Okay, so we have two problems here. The first one is this define, which I anticipate to you that cannot be completely eliminated, unfortunately. So you have to, in some sense, use some macro or something else for telling that one class can be visitable by accepting visitors. And this cannot be avoided completely. But what is more important is to try to remove this dependency here as much as we can. In particular, as we have seen, the visitor as it is now depends on every single class in the element hierarchy. Because I have to implement these virtual visits for every single class, okay? And that's not very nice, unfortunately. So if we could, in some way, make everything a little bit more less dependent on the element hierarchy, that would be nice. And fortunately, one solution in this sense has been provided by this researcher. His name is Alexandrescu, who wrote a book called Modern C++ Programming, something like 10 years ago, a little bit more maybe. And this book has a lot to do with templates and template metaprogramming. Okay, so we are going to see one technique for trying to remove a little bit this dependency that uses templates a lot. First of all, I would like to remember that we cannot have template virtual functions. So I cannot write things like template class T and then inside do a dynamic custom T and things like that. No, I cannot do that because this is a virtual function, and a virtual function cannot be templatized. So unfortunately, I cannot do that. So I have to, unfortunately, to use this macro. I can do something about the visit. Actually, I can define one different visit for every type of node. Unfortunately, they cannot be virtual anymore, so I need to do something a little bit differently. So let's see. I've taken this from Stack Overflow. There was a question, and the question was that the guy would like to handle any type. So he would like to have a sort of visit for every single different type and accept for different types. So of course the code that he did was not working. So one of the answer was saying, okay, from this book, Modern C++ Programming, Design, Generic Programming and Design Patterns Applied by Andrei Alexandrescu. By the way, is one of the books that I suggest you to look at if you want to get more informed about C++. So let's look at the technique. So we have a base visitor, which is just a single class, and then visitor, which it's instantiated with respect to a class T and a return type R, which normally is an integer, and implements a visit in this way, and this is a virtual function. Okay, and then base visitable, it's basically an element that wants to be visited. And the interface is made by a function accept which may or may not return something, which takes a base visitor reference, and by default it just returns nothing, so 0. Then we define a macro visitable, which implements this accept in the derived classes, and it implements by calling accept visitor. And accept visitor is the one that is static and templatized and takes the guy to visit and the base class, and it tries to dynamic cast these to visitor t. And if it works, then it calls visit. So it's a sort of extra indirection to call the correct visit by using a dynamic cast on the correct type. Okay. So we select the type by just doing a dynamic cast. And finally, we have example of uses. For example, I want to make an element which must be visitable, and this must derive from base visitable and implements visitable. And visitable2, it's also derives from base visitable and implements visitable, and so on. So this extra indirection here is to avoid strict dependency between the object, the visitable, and the visitor. So basically the pattern is just these few functions: base visitor here, visitor, and base visitable. So these three classes are enough for implementing the visitor pattern. So it's not very easy to follow, I know. Actually, the patterns by Alexandrescu are always very, very difficult. So you can go and look at this code to try to understand it with a little bit more time. You need to understand all the subtleties. Instead, I would like to show you another use of the visitor pattern into a library which is called boost variant. Okay. So first of all, the boost libraries are a set of libraries which are made available by a non-profit organization which maintains these libraries, and these are more or less standard in the sense that many of the libraries in the boost library eventually became part of the standard library. Examples are the shared pointers were initially available in Boost, and later they moved to the standard. And also the thread library were initially available as a Boost library and eventually moved into the standard. So it's an interesting class of variables, libraries, sorry. And it's nice because it looks like a sort of pre-phase before getting into the standard. Okay, so the Boost library is quite complicated because it contains many libraries, and not all of them are very useful. So you must know which one to use. The one we are going to look at today is variant. So the idea of this library is to provide a way to implement what are called union in the standard C. So in C, C++, you have the concept of union. A union is a data which can be seen as two different things, either an integer or a double. Okay? For example, you can write u.d equal 3.14. And then you can write u.I equal 3. Now, u.I equal 3 overwrites ud. In fact, there are not two different separate locations in memory for I and d, but there is only one that can contain either I or d, but not both at the same time. So it's a union is a sort of data which can have several types. Depending on how you are using it, it can be one or the other. Okay. Now, the problem is the type. First of all, union can only contain plain old data, so primitive types, integer and double. It cannot contain objects like string. You cannot write this. This is illegal. Okay? And so it's not very useful in object-oriented when you want to have one element which can contain several kinds of data. To do that, you need a different approach, and this is provided by this variant. Okay? And here you have an example. You have a boost variant int string. U hello world. So now U contains a string. And later on, you can change and make U equal 5. And then U will contain a 5. Okay? Now you would see that actually there is something called boost apply visitor, which is the thing we are going to see now. It's actually for visiting the object, we actually apply a visitor and see what's the result. So for visiting and understanding what's inside, the developers of this library decided to apply the visitor pattern. So here I'm basically rewriting the same example and showing you what is this visitor. So in the main, I'm doing a boost variant int string variable, and the visitor is the visitor I'm going to apply. And then I have a variable 5, and then I print the variable, and then variable, this is a string, and then I print the variable. And this works because the variable can be either an integer or a string. Okay? And I would like to see what this variable contains at a certain point. So I apply the visitor pattern. And I write a class visitor, which derives from boost static visitor. And it provides two operators, parentheses here. The first one takes a reference to an integer and prints this is an integer. And the second one takes a reference to a string and prints this is a string. So what happens is that when I do boost apply visitor variable, if variable in this specific instance contains an integer, the first function is going to be called and will print this is an integer. If variable in this specific instance contains instead a string, the second operator is going to be called and prints this is a string. Okay? And I can have also a vector of variance, and the vector of variance contains 10, then people, Pluto, 25, 7, Paperino, and then I do a for cycle on the vector and apply a visitor to all of them, and this is going to print what it contains every time. Okay? So. Okay? So this is all the printing and how it works. So this is a version of an implementation of visitor that works for the boost variant. As you can see, visitor here in this specific case has been implemented so that it's independent of the type of variable we are doing here. You can use also your own class, and the visitor is always going to be the same. So they applied a technique very similar to the one by Alexandrescu for separating the visitor from the actual type that is going to be in the element. Okay, so to make a summary, if you look at the classic implementation of a visitor by using only object-oriented without any template, strange template mechanism, you are going to run into the problem that the visitor depends on all the elements in the hierarchy because of this list of visit function. And so this tight coupling between visitor and hierarchy makes it difficult to add the new elements in the hierarchy because you have to change this base visitor and every single visiting class. By using quite complex template patterns, you can avoid that. And one example of these complex template patterns is in the bus variant library, which separates completely the implementation of a visitor from the actual type that is going to be visited. Okay? So, quite neat. Okay, so this is everything about the visitor, and let's continue now with another pattern. We are going to see another pattern. It's called the interpret pattern. So it's a pattern that can be used for writing an interpret of a language, or for writing a parser, or for writing things like that. So motivation and example. Given a language, a programming language, define a representation for its grammar along with an interpret that uses the representation to interpret and then maybe execute sentences in the language. Now, in many cases, it is useful to define a small language to define things that need to be expressed easily. Examples where a simple language may be useful: configuration file for creating objects, list of complex parameters, rules to configure filters, and so on. For example, in the second assignment, I asked you to save the objects, the shape objects on a file, and then later on to read from the file to create the objects. So there you need a very elementary, very simple parsing. You need to read the content of the file and create the corresponding objects. So objects can have different types and of parameters lists, so you need to interpret the parameters. Okay? If the language is complex, for example, a real scripting or programming language, then it's better to use classical tools like parser generators. However, when we want to implement a simple thing, then it may be useful to do it by hand using C or C++. In the following example, we will assume to build a simple interpret for regular expressions. So you know what is a regular expression, maybe. Anyway, it's not very important. A language is often expressed as a set of grammar rules. The grammar rules are similar to the ones I show you here. Basically, they can be seen as a sort of tree-like structure, or sometimes recursive. So, for example, here we are saying that an expression can be consisting of a literal, or an alternation, or a sequence, or a repetition, or another expression within parentheses. And a literal is just a character, or a sequence of characters. An alternation is an expression followed by symbol vertical bar followed by another expression. And the sequence is an expression followed by symbol ampersand followed by expression. And the repetition is an expression followed by symbol star. So we call those ones rules for generating the grammar. And the idea is that these one are the rules that tells us, first of all, if a specific program is correct, and second, they give us the structure underlying one specific program. Programs in this case are a regular expression. We want to read this regular expression, transform that into an internal representation that is going to be an abstract syntax tree, and later on do something about it. So this interpret pattern complements very nicely with the example we have seen before about the visitor. In the visitor, we already had an abstract syntax tree, and we wanted to do operation in it. With this pattern, we want to read a file and build the corresponding abstract syntax tree. And the abstract syntax tree is described by these expressions. So to implement the previous grammar, we prepare a class for each rule. And each class is derived from an abstract classes. At the end of the parsing, we must obtain an abstract syntax tree that will represent the expression. So here is the pattern. At the top, you have the rule, the class that represents the top rule, which is expression. I call this class a regular expression, and I implement one function called interpret. And then I have literal expressions, sequence expression, repetition expression, alternation expression, which are all types of regular expression. And of course, each one of them is a little bit different. A repetition expression internally contains a repetition of regular expression. A literal expression, it's a leaf, it only contains literals. A sequence expression is just two regular expressions, one after the other. And alternation is also two regular expressions. Okay, so you can see that there is a very similarity between this and this pattern here. In particular, an expression is a literal, alternation, sequence, repetition. So it's a literal, repetition, sequence, alternation. And an alternation is an expression followed by a symbol by another expression. So an alternation contains two other regular expressions, and so on. So it looks very similar to the composite pattern, right? And it's the way you implement a structured tree that represents the abstract expression. And we have already seen this in the examples before when we implemented these nodes. And in particular, here I have number node, variable ref node, assignment node, sum node. And we have a class node, which is the top class. And then we have variable ref, which derives from node, it's a leaf. A number node, again, it's another leaf, derives from node. And then we have a binary operation, which is just a generalization between assignment and sum. So we could actually write the grammar for this by, it's going to be quite easy. So the grammar for this specific thing would be something like node can be what? Can be a number or a variable or a binary operation. Then you write the number is just a number, so you have to specify all possible kinds of number, okay? And then you have to say var, and you have to specify how to parse a var, because it's another leaf node. And then you have to specify the binary operation. It's either assignment or a sum, and then assignment. It's something on the left, so it's a node, followed by an equal, followed by another node. And then sum, it's very similar. It's a node followed by class, followed by another node. Okay? So this is the grammar for our simplicity. And so from this grammar we can derive structure. So there is a correspondence almost one-to-one between these and the hierarchy classes. So the abstract syntax tree must be built by a parser, which is not part of this pattern. And once the tree is built, we can use it in our program. For example, we could pass the interpreter a sequence of characters, and it will tell us that the sequence respects the regular expression. We would also print the expression, transform it into another representation, for example, a finite state machine. So the general UML representation is the following. We have a client with a uses a context, and then the abstract expression. And typically you have either terminal expression, like number, variable, or in the case of the regular expression, this is going to be a literal, and then non-terminal expression, which refer to the abstract expression. And actually it can be also a little bit more complicated than that. So the participants in this pattern are the abstract expression, in this case regular expression, which represents the abstract interface for the node in the tree, the terminal expression, which represents the leaf of the tree, and the non-terminal, which is just a rule in the grammar, and so the median node in the tree. Context is something that contains global information that can be useful for performing the main operation. And the client, which builds the abstract syntax tree via parser and calls the interpret operation to carry on the interpretation of the language. So it's quite easy to change and extend the grammar, because you can write classes, extend existing classes, and modify whatever. It's quite easy to implement the grammar, because as we have seen, there is almost one-to-one correspondence between the path, the rules, and the structure of the hierarchy. However, when things get complex, it's a lot of classes, and also it's not very efficient to execute the language. So maybe if you have something very complicated, the approach to be used has to be completely different. Has to be something that has to do with compilers, basically. And finally, since you have the tree, you can do many things with it. For example, you can use the visitor pattern to implement a new operation without modifying the classes. Examples of parsers. Later in the course, we will analyze a tiny parser in C++ that I wrote some time ago. And you can find it at this GitHub repository here. And well, if you want, you can try. Unfortunately, the parser has a very serious bug. So if you want, you can go and look for it. And if you find it, I'm willing to give extra points at the exam. Okay. So it's there. It still contains the bug. I did not solve it yet. So if you want, you can go look into it and try to understand where is the bug. Okay, last one we are going to do today is the command pattern. And the command pattern is actually something that more or less we have already seen. So sometimes it's necessary to issue requests to objects without knowing anything about the operation being requested. For example, when pressing a button, something happens that is not related or implemented to the button class. we've already seen this when we have seen the adapter pattern. So the button should not know anything about the target of the button press. If the target is a document that should be printed, well, the button doesn't care. It can be anything, but the button should be independent of the specific operation. So we have already seen the adapter pattern for doing this, but in general, you can have also that exactly the same operation can be performed by a menu item, or by a button in a toolbar, or by something else. So we want to generalize the concept of executing an action into something more general than just a button. For example, this same program I'm using today for visualizing things, it contains buttons here, like for example these zoom buttons. And you can do the same by clicking on the menu, and the same action is going to be performed. You can zoom either by clicking here or by clicking here. Okay, so it's exactly the same action you find in two different places. So how to implement this? One way to do that is actually useful for many other things is to encapsulate commands into objects. And you can do many things with this in this case. For example, you can do undo and redo operations of commands, or you can compose several commands into one more complicated command, for example macros and things like that. So if the function can be seen as an object, you have a lot of advantages. Maybe that's not always useful, but in general it can be very advantageous to have a function encapsulated into an object. So the example about the menu I've seen before is that you have a command, for example a copy command or a paste command, and you can put that into a menu item, which is put inside the menu, which is used by the application, and the application uses a document. And so the copy command will execute something on the document, and the paste command will execute something on this other document. So the idea is that all the functions you can do on the document, you can abstract them into an object command, which derives from a base class command, which implements an execute function. So, and if you want to have a macro, so a list of commands, well, you just apply the composite pattern, in which you can have basic commands, and then you can have a list of commands here in the macro. Okay, so when you want to execute the macro, you just execute in sequence all the commands inside the macro. And then they can be themselves macros, so you can have a hierarchy of commands, one inside the other. Okay, so the general UML structure for this is that you have a command base class and then concrete commands. And the invoker, it just calls the execute on the command, and the concrete command already knows who is the receiver, and so it's going to act on the receiver. And additionally, it can also contain some state, so while it acts on one or more receiver, it can update the internal state to take into account the history. So I just said that we can implement undo and redo. Of course, this is not always possible. It depends on the operation. So the operation should be reversible, of course. And we can do that by adding undo and redo operations in the command abstract class. And so the command in general may need to carry additional state of the receiver inside. For example, if I'm modifying a document, I may store the previous state of the same document, or I can store exactly the operation I did so that I can undo them and go back to the previous state when I want. So we need an history list of commands that we do and undo. And it's of course important to understand how far we can go with this history. One way also to implement this command is to use what is called the prototype pattern. The prototype pattern is a pattern that says that for creating new objects, we just copy existing ones. So we create initially, at the very beginning, one object of type command, and then we call a clone for prototype for copying it, and then customizing it with the internal state of the receiver, and then save the copy on the history. There is a huge difference between commands and callbacks. A callbacks is just a function, so it has no state. Instead, commands are objects, not just functions, so they have states. So they can carry state information on the receiver, they can carry information on the history, and in general you can do many things like copying and so on. The invoker only needs to know the general interface of the command, so the function execute, and not the internal information, so parameters, which are decided at creation time. And so I'm going to show you an example of a command. So in C++, typically the command pattern is implemented by having a class and overloading the operator parentheses here, which acts as a function. Okay, so this compare is an operator which returns true when A is greater than B. Okay, and you can do the same with a simple function, myCompare. Then we have another command here, or if you want, you can call it also function object, which is initialized with the sum value, and then it's going to print the sum of the internal value with the parameter that is passed to the operator. And finally, we have sum, which is initialized to 0, and every time the operator is called, it just sums the current number to the internal variable, and then at the end you can get the result. So let's see how we use this. We have a vector of integers. We push back 20 numbers randomly selected using function rand. And then we have object P, which is of type print, and it's initialized to 100. And then we are going to print all the elements inside the vector, and we are going to actually apply function object P to all the elements of the vector. And then we sort them, and then again we apply P to all the elements of the vector. And finally, we just we could, for example, sum of the elements in the vector, and then print the sum. Okay. Okay, so the sum didn't work very well, sorry, because I have to write like this. Okay, so command, I just printing all the numbers after summing 100 to all of them, and then I just sort and I print the same in sorted order. And finally I do the sum, and the sum is 1188. I did this because if I write this, what happens is that S is passed by value. That means that a copy of S is passed to function for each. And the copy of S, you call the operator on the copy of S, and the copy is deleted when the function is finished. And so basically we summed something to this internal S, and then this is of course destroyed afterwards. To avoid this kind of problems, one way to do that is to avoid the copy operator. So this means I forbid the copy of this element, of this object. Okay? So by writing equal delete in a standard C++11, it means that the copy constructor is not implemented. So now the compiler will tell me that it doesn't work because I'm trying to pass S by value in a for each here, initializing argument 3 of for each funct. And it's trying to make a copy of this sum, but it doesn't work because I cannot copy this object. So maybe in this way I realize that I'm doing an error, and so I'm forced to write this. This means for each should not interpret the type of the third argument as a class, but as a reference. So now it works. I'm not copying S, I'm just passing its reference, and so everything works as before. Okay? In modern C++11, actually writing a class just for summing numbers is maybe not the case. One way for doing that is to use lambda functions. So I initialize a variable mySum equal to 0. I call for each, and I use a definition of lambda function. So this means for each should be passed a function. But I'm not writing a function just for this. I'm writing a function on the fly. That's a lambda function. It's a named function, a function created on the fly. And this function is going to act on a variable mySum, which is defined in the environment. And it will use one parameter x, which is passed by the for each. This x is actually every single element in the vector. And so I'm going to sum this to mySum, and then I print it. And, okay, and of course I get the same number by summing with llama function. In C++11 is much more easy to have to do with this command and functions, and we are going to see more examples tomorrow afternoon. So we finish for today. We stop here, and we will continue tomorrow afternoon at 3:30. Okay? Okay, that's it for today. Thank you very much. See you tomorrow.
Right?